we've been talking about waves and particles that can be waves and waves that can be particles. And so we have the last time discussed that it has to make sense when you have a particle and you associate a wave with that particle. That particle has to be a quantum mechanical particle. So you can't assign a wavelength to a truck or to yourself. You can't assign this, but it doesn't make any sense. Okay? So these are very small particles. They behave with quantum mechanics, after quantum mechanical rules. So we also have seen that when we describe the electron, or we want to describe the electron around the nucleus, we need to have a standing wave. And I've shown you that standing waves, they are only multiples, whole number multiples of a half a wavelength would be, or multiples of a half a wavelength would fit in a standing wave. So the lowest possible wave you have is, or waveform is half a wavelength. And with this we have assigned this has quantum level 1, n equals 1. That's the lowest possible level that, for example, an electron around the nucleus can have. So n equals 1, it has energy. It has kinetic energy. Okay? That's called the 0 point of energy. Okay? It's not zero then energy, but it's the lowest energy that an electron can have around the nucleus. Okay? That's quantum level 1. And then we have seen that energy travels or is given off or taken up in packages. Whole number multiples of n. N equals 1, n equals 2, n equals 3, n equals 4. And so I would like to demonstrate this with you, to you here with this instrument here. And so we put a standing wave in here and here. Okay? Has to be 0 here, has to be 0 here. Otherwise it's not a standing wave and we don't hear anything. So did you notice something? It didn't go zzz, the sound. It went low, higher, 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 highest. Okay? So even this is quantized. There's only certain wave functions that fit in there. N equals 1, n equals 2, n equals 3, n equals 4, and so on. Okay, I can't do it so fast that we get to n equals 15 or something like this. But this sort of illustrates this, that you have quantized energy, and in this case it was sound energy, taken up or given off. So at the end, we have talked about an atom. And that atom has electrons. And these electrons, they are specific for that atom, and they can take up energy, but only a certain energy. That energy has to fit within this electronic scheme. You can bring that electron, it takes up energy, you can bring it in the first excited state, where n equals 1 to n equals 2. You go in the second excited state, it's n equals 3 to n equals 4. Okay? And to do this, you have to have the right energy, the right wavelengths that it can absorb. When an electron absorbs energy, it will be lifted in a higher energetic level. So, and I have shown this to you, that we have certain wavelengths, they don't fit. So that cannot promote that electron in a higher level. And some of them, when the energy difference between one level and the other is exactly that energy of that wavelength, or of that wave that you are shining on it, then it will promote it to that level. And vice versa, it will, when you have it in an excited level, if you excite that electron, it has to come back down. So how does it come back down? It emits light. And depending on the level where it comes from, it emits a certain light, a certain frequency, a certain energy of light related to the level differences. From the level it goes, from the higher level to the next lower level, or 2 levels down, and so on and so on. It has to fit. Now, I have here a mercury lamp, and I hope that Karen will show up. If you could have the camera, please, on that. I think the instruction's been given. I have a mercury lamp. This is nothing but mercury. Mercury is liquid at room temperature. And you put a heater under there. So it will evaporate. So that means that the mercury atoms taking up energy. And in fact, the electrons are taking up most of the energy. They get into excited states. And then, of course, they go down again and emit that light. And to us, that light looks pretty bright, and it looks nearly white. And so that means it emits certain wavelengths of light. And I want to show you these wavelengths of light if I can get a hold of Karen. So we heat the mercury. You see this is the mercury vapor lamp. We heat it, it goes up to 200 degrees Celsius, so it says hot here. Actually, it says in German, heiß and slash hot, so that you don't grab it, all right? That's why they put the shield in front of this, that you don't touch it accidentally, and that you also don't lock in the bright light. So this emits light of several wavelengths. Remember, that light here had a lot of different wavelengths. When we split it through a, what we would call it, a prism, for example. We split it up and see the individual wavelengths. We do the same thing here. We have the prism, and then let's look how many lines we have emitted. And this is nothing but we had discussed the last time. It goes from a higher state to the lower state, okay? And by doing so, it emits photons, and photons are light, and light is energy. E equals h times nu. So let's have a look at this, please. So we are ready. Okay, okay, if you could have that light off, please. There's not a lot going on here. So far, how many wavelengths do you see, or how many emission lines do you see? You see one here, okay? You see one here, and if you look very closely, it's very bright. There's somewhere a blue line here. You see that? Purple, okay? Purple line, all right? So, I see blue, actually. Okay, it's blue, but so it emits 3 lines. Mercury emits 3 lines. If I heat it up, excited, it emits 3 lines. But actually, it emits more than 3 lines. We only can see 3 lines out of our eye. So what I have here, I have a screen which is sensitive to ultraviolet light. And so ultraviolet should be here somewhere, isn't that right? The energy increases here, should be here. So if I put that up here, you see that here in the front? Can you see that there's a line here? You see that? Yeah. Yeah, of course, this one is even better. But this one, you see here, there's one which we can't see. There's 1, 2, 3, 4 wavelengths are emitted of different energy. Did you get that? If you can have the light back up, please. So Karen said he can do this by himself. He doesn't need me. And she was perfectly right. But I feel safer when Karen is around. Okay. All right. So you have seen the emission of light. The electrons took up the energy, the heat energy, promoted the electrons in higher level, in higher quantum levels, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. And then it emitted it, obviously, from 3 different levels. Actually, 4. And so that one in the far side, that the ultraviolet, that must have been the highest state, because it's the highest energy. It came from a high level to the ground level. Then the second one was a little bit lower, but it was still high energy. The third one, what was the third color? What was it? What was the third color there? From the left, the second. From the right, what was it? What were they called? Orange, and then it was green, yeah? Okay. The green one is even lower. And then the last one, what was that? That was the orange one, wasn't it? Close to red. Of course, that's a very long wavelength. It's a very low frequency, which is the energy is low. So that's why it must have come from a lower level going to the ground state. We don't know what level this is, but you're going to learn this, because at least we're going to try to teach you that. So at the end, and this pertains to what I just talked to you about, at the end of the last lecture, I asked you this question, did I? And so we have a level 1, n equals 1, primary quantum number 1, 2, and 3. And this is level 1. This is the energy. The energy increases here from the lowest level is 1. The energy is not zero there, but it's the lowest possible level. And now we have 2 and 3. And I want to know from you which line arises when I go from 3 to 1. Is that C, B, or A? There's other possibilities that you have transitions from a higher to a lower state, which 3 to 1, obviously, you think about it, okay? Why don't you give me the answer? No, you discuss it with each other, because the last time we had it posted, and now you can discuss it with each other. Yes? It can move from 3 to 2 also. That decides the energy that it wants to emit. That's a difficult issue. Okay, 1 second. 440. Yes, good. So let me go through this for you. So you have 3 possibilities. That's the smallest energy difference. If it goes from 3 to 2, it emits relatively low, the lowest energy line. Okay, that means it has the longest wavelength or a relatively low frequency. That would be C then here. Now if you go from 2 to 1 or from 3 to 1, which one has the high energy? 2 to 1 or 3 to 1? 3 to 1. So if you go from 2 to 1, obviously this is higher energy than if you go from 3 to 2, but not quite as high if you go from 3 to 1. All right? So that must be this here. And now you go from 3 to 1, that must have the highest energy. E equals h times nu, so it has the highest frequency, or delta h is delta h, delta nu. So that means this one here must have the highest energy, A. There you go. And that was the answer. Let me go and get to this. What did I do with it? I lost it. I wanted to give you the overview, and the overview is actually here, okay? So today, we're going to discuss in detail an electronic system. We discussed the hydrogen atom. How many electrons does it have? Hydrogen atom. How many electrons does hydrogen have? We're discussing a 1 electron system. Always keep in mind, today we're going to discuss 1 electron systems. And so, you know about the uncertainty principle? No, you don't know about the uncertainty, but you know about the de Broglie relationship. If you have a particle, you have mass and velocity gives you momentum, okay? And if you have a wave, you have a wavelength, and you can calculate the momentum. Or vice versa, if you have a particle, you can calculate a wavelength. Has to make sense. So these waves, you can express those mathematically. How do you express those in terms of trigonometric functions? A wave, what would be a wave function? Sine or cosine, exactly. So this is a wave function, it's a constant times the sine of something like this here. There's a wavelength and there is x is the distance here. And so you can define this with a wave function, this wave. You can write a wave equation and can define this. Now, the question is, I know lambda very well. So I know the wavelength of this wave quite well. But we said this is also the, so I know the momentum when I know lambda, I can calculate the momentum. I have 1 momentum, okay? But if I square that wave function, I get rid of these lobes here. And it looks like this. It's just a mathematical equation or operation. And we have squared this now. And now this wave function here, that wave, shows us the probability of finding that electron. So that because I have a given lambda, that electron can be here, somewhere in between here, not here, somewhere here, somewhere here, somewhere here, somewhere here, somewhere here, not here. When it goes to 0, I know that it cannot be. But where this is positive, the lobe, I know it can be somewhere there. So it can be everywhere. You see that? Because I know only 1 wavelength. So I don't know its location very well. I have an uncertainty in the position. Where is it? So I can't describe this with 1 wave function. So now I want to construct a wave function where I know this is my wave function here, and I have here a very high probability that electron is there. So there's very low probability, but here's high probability. So how would I construct such a wave function? I have to take a whole bunch of waves and superimpose them, or add them together. And then I can make a construct like this here. And so then I know the position quite well. I know where that electron is. And so the wave function for such a wave function where I want to know where the electron is, it's a sum of a whole bunch of waves, okay? And they have, of course, a whole array of different lambdas, different wavelengths. With this, I don't know my momentum. So if I can either know the position well, or I know the momentum. So this is a dilemma. And we call this dilemma the uncertainty principle. What this means is, so I can square this again here, then you see it could be very little possibility that it's here, probability that's here, but there's a high probability that the electron is here. Okay, it's not 0 the probability here, but this is a high probability. So I have an uncertainty in momentum, as I said. So the uncertainty principle is the Heisenberg's uncertainty principle. He did this in around 1925. He said the uncertainty in my location times the uncertainty in momentum has to be larger or equal like in a finite number. And that finite number is h over 4 pi. That's what it is. You just have to swallow this. So what this shows you, if you know where the electron is, you don't know what its momentum is. And you know the momentum is, you have 1 momentum, you have no idea where the electron is. So it has to be somehow a combination of both of these things that we can give a probability where we can find that electron. And this is done with quantum mechanics. There was a fellow by Schrödinger. I think Heisenberg actually lived not in 1901 to 1975. I think it was Schrödinger who lived at the time. And Schrödinger, and it was not 1925 when he came up with the uncertainty principle. So the Schrödinger, he said, okay, I have these waves. Now, how do I connect these waves of this particle, and in this case the electron, with energy? How would I do that? And so I want to know, what is the energy of these waves at a certain level, n1 and 2 and so on and so on. So this, I'm going to briefly show this to you. So this is a wave function multiplied with a bunch of constants, and I take the second derivative of this here, of that wave function, okay? It will be the test. No, just kidding. Okay? I just want to give you the principle that you heard of the Schrödinger equation, that you know what it is. Who's in physics? Yeah, you know all this already? You solve these equations? Did you solve them already? Yeah, okay, good. It's pretty complex. I do it only in one dimension here. And so that's why we have only, there's X, Y, and Z. There's three more dimensions. We do it one dimensional at the moment. So this gives you essentially the kinetic energy. So that's the wave function. I do something with the wave function multiplied with a bunch of constants, gives me my kinetic energy. That's what Schrödinger said. But we also have potential energy. Kinetic energy is the movement, the energy of the movement. The potential energy is essentially the interaction between the nucleus and the electron. And this should be always sort of the same, the potential energy, because the nucleus doesn't change. So that's the potential times that wave function. And what this gives you, so the kinetic and the potential energy gives you a wave function, that wave function again, specific wave function, and the total energy of the system. That's a differential equation. So you can't do much with that, but I just wanted to show you this. And we are actually mostly interested in the kinetic energy, because potential energy we said essentially is constant. We're looking at kinetic energy because these electrons move, and we want to know what is the energy of these electrons. How can we describe that? And we do this today. We're not solving the Schrödinger equation for a one-electron system, but I give you some solutions to that. So what you do is, you have a Hamiltonian. You say, okay, I have my wave function. I do a bunch of mathematical operations with this. That's a Hamiltonian. It gives a set of instructions. That's what I do with this wave function. I have a certain set of instructions. I get that wave function again times the energy of that wave of that system. So of course there's more than one solution. There's a whole bunch of solutions, especially if you have more than one electron. There's a whole bunch of solutions. And today we're going to talk only about one solution. But when we have multiple electrons, there's very, very complex solutions. And I will give you the solution in terms of pictures, in probability of the electron being around the nucleus, how they travel around the nucleus. Probability that you can find it somewhere here, but not here. I'm speaking in riddles, as you can see, but this is called orbitals, these probabilities. When you depict them, you call them orbitals. And we talk about this the next time. So the wave function, the energy is, and this I'm just want to discuss only the kinetic energy. We have seen this here. This is the second derivative of this. It gives you the total energy, and this is actually the wave function itself. Okay. Now, the solution for this, if I have a one-electron, one-dimensional system, the solution for this is a bunch of constants, is n. Remember what n was? The quantum level. N equals 1, n equals 2, n equals 3, n equals 4. That's the principal quantum number. And then the mass, of course, the mass doesn't change as an electron. And the length of the box, you see this was our box here. The length of that wave, where the boundary conditions apply. If you have larger and larger system, the box gets bigger and bigger. All right. So this is what we see. The energy of the nth level is a bunch of constants here times n squared. The nth level squared. So let's see if n e equals 1, then we have a constant here. And what would it be? What would be n squared would be? Would be 1. Okay, so that would be down here. That would be our wave function. We've seen it before. That was the lowest possible shape that the wave can have. If it doesn't have the shape, half a wavelength, it's not a wave anymore. So this is why this has energy. This is why at level 1, you still have energy. Kinetic energy. And this is the 0-point energy. We call this 0-point energy. Now if you square this, it looks like this here. Okay, fine. So the next higher energy that electron can have would be n equals 2. So that would be n equals 2. That would be a full wavelength. Okay, and if I square it, would look like something like this. And n equals 2, it should be something like 4 times that constant here. All right. Now we have n equals 3. So what would that be? How many times the constant? What's n? N equals 3. N squared is what? 9. So it should be 9 times that constant. So that would be 1.5 wavelengths. And the probability would be looking like this. And now we have n equals 4, and we can go on and on and on. 4 would be 16 then, as you see here. And this would be the wave function, and this would be the probability of to find that electron in that wave function, in space. So we have seen this here now. This is our relationship. So n is the principal quantum number. N equals 1, 2, 3, 4, 5, 6, 7, 8, to infinity. And when we have reached infinity, then the electron has left the atom. Okay, actually, and this is the energy 0 then. You see that here? This is that bunch of constants that I just showed to you. And this Z, what is that? Or Z, what's that? That's the atomic number. But we're only dealing with hydrogen today, or at least now. What's the atomic number of hydrogen? So this is a 1, and you square it, it's still a 1. Now n can be 1, 2, 3, 4, 5, 6, and so on, depending how high you get in levels. Times r is an energy, is these constants, we call this the Rydberg constant. And the Rydberg constant you can express in joules or in hertz. And if you take a mole of electrons, then you have it in kilojoules per mole. Okay? So we're talking at the moment about 1 electron. The Rydberg constant for 1 electron. So let's construct the levels of hydrogen. N equals 1. What do I have here? How many Rydbergs? That's a Rydberg. What do I have to multiply Rydberg with? -1. Yeah? This is the ground state. It's -1 Rydberg. So I say minus. Remember? There's a minus. What's the next level? N equals 2. What is it? -1/4 Rydberg. N equals 3. -1/9 Rydberg. And so on and so on. And you come, if you give it more and more energy, that electron, eventually, you give it enough energy that it will leave the atom. And then you have it ionized. And when it leaves the atom, by definition, the energy is 0. So this is negative here. It's just a matter of definition. You have it negative. That's the energy you have to put in order to get it to higher energy states. If you put exactly this amount in here, then you have it ionized, and it's an ion. The electron is gone. It left the building, or left the atom. Okay? So this is all pretty confusing. We're just calculating these energy possibilities, energy levels of a one electron in hydrogen. That's all we are doing. Let me ask you a question. Now, it's tricky, of course. If you have helium, so obviously this is a helium anion or cation? Cation. So that means it's positive. If it's positive, how many